Welcome to our discussion of nuclear chemistry and radioactive decay. In this video, we're going to identify three main types of radioactive decay, write balanced nuclear equations for each type of decay, and then describe the purpose of each of the three types of radioactive decay. Recall from our last video that radioactive decay is simply the disintegration of an atomic nucleus through the emission of subatomic particles and or photons, and photons being those packets of light energy. As far as these subatomic particles, there are three main types of subatomic particles that are going to be emitted during decay, and they are alpha particles, beta particles, and gamma rays. Alpha decay is the first type of decay we're going to talk about. And alpha decay occurs when an atom with a nucleus that is too big emits 2 protons and 2 neutrons in an attempt to slim down and become more stable. These protons and neutrons that are emitted are called an alpha particle, and it's a positively charged particle that, because it has 2 protons and 2 neutrons, it's actually the nucleus of a helium atom, which is why we represent it with the shorthand for a helium nucleus. It's also represented by the Greek letter alpha. So now let's take a look at how we might see questions about alpha decay asked on a quiz or a test. So example number 1 says that nuclide francium-220 undergoes alpha decay, and they want us to write the balanced nuclear equation. Well, we know that we first of all have our francium 220, 87, and this is a particular isotope of francium, and it's undergoing alpha decay. So it's going to emit an alpha particle, which we stated was simply 2 protons and 2 neutrons, or the nucleus of a helium atom. And our decay equations are always going to have our emitted radioactive particle on the product side, because we're emitting it from whatever isotope we are starting with. And from our nuclear chemistry introduction video, we said that the sums of our numbers for our top and bottom numbers, our atomic masses and our atomic numbers, have to be the same on the product and the reactant side. So if I have 220 over here on my atomic mass, I have to have a total of 220 over here between my alpha particle and whatever my francium isotope is going to become. So 220 minus 4 is 216. And the same principle applies to my atomic number. So 87 minus 2 is 85. So I know I have something with an atomic mass of 216 and an atomic number of 85. Well, if it has an atomic number of 85, it has to be the element astatine. So this is the balanced nuclear equation for the alpha decay of francium-220. I have my francium-220 decaying into an alpha particle and undergoing our transmutation into astatine-216. The next type of decay we're going to talk about is beta decay, which happens when an atom has too many neutrons and not enough protons. During beta decay, a neutron actually becomes a proton, and a supercharged, super fast electron gets emitted, which is our beta particle. This beta particle is negatively charged and is represented by the shorthand for the electron, which is an E and a 0 since our electron has no mass, and a -1 since our electron is negatively charged. Or it can also be represented by the Greek letter for beta. So let's take a look at a practical example using beta decay. So example number 2 asks to write a balanced equation for the beta decay of phosphorus 32. So we've got our phosphorus undergoing beta decay. So we know that our phosphorus is going to be our reactant, and since it's decay, our radioactive particle, our beta particle, is going to be on the product side, and we're going to use the shorthand of our electron. And we know, once again, our numbers for our atomic masses and our atomic numbers, the sums on the reactant and product side need to be equal. So I have 32 on my atomic mass for my reactant side, so I need 32 on my product side. And since my beta particle has an atomic mass of 0, the atomic mass on whatever this newly formed element is going to be needs to be 32. And I have 15 on my reactant side, but I have -1 over here. So this number -1 actually needs to be 15, which is a little different from our beta decay. So this, my atomic number for this element, actually needs to be 16, because 16 minus 1 is 15. So when I look at my periodic table, the element with the atomic number of 16 is sulfur. So my daughter nucleus, my daughter element, is going to be sulfur 32. The last major type of radioactive decay we're going to talk about involves gamma rays. And gamma rays are emitted when a nucleus is in a very excited state with a lot of energy. So they're going to release a photon to get rid of some of that excess energy. In fact, the helium that makes up our sun is constantly decaying and emitting gamma rays in the form of light. So gamma rays are unique in that they aren't actually particles. They're high energy photons or packets of light, and they have no charge. So we represent gamma rays with the Greek symbol gamma and a 0 and a 0 to represent that it has no mass and no protons, because it isn't actually matter, it's just energy. So a radioactive decay equation involving a gamma ray or gamma rays might look something like this. I have my thorium decaying into radium and an alpha particle and emitting a gamma ray. So this is actually both alpha decay, and this is letting us know that in addition to emitting a subatomic particle, we're also emitting a photon, which we talked about early in the video is always a possibility. We can either emit subatomic particles or light rays or energy or photons, or both. And in this case, we are emitting both an alpha particle and gamma rays through radioactive decay. There is one last type of radioactive decay worth mentioning, and that's called positron decay. Positrons are the antiparticles of electrons. They have the same mass but different charges. So we actually represent our positrons with our electron and our 0 for our mass, but a positive one since they have a positive 1 charge. And they're going to be, positron decay is going to be the opposite of beta decay. So if we were to look at an example of positron decay, if we have our fluorine 18 undergoing positron decay, it's going to emit a positron, and it's going to become oxygen 18. So this is just a quick example of positron decay. You won't see it often, but it will come up every now and then. Just remember that positron decay is the opposite of beta decay, with a positively charged particle with no mass. So to review what we've covered in this video, in alpha decay, the sum of the atomic masses and the sum of the atomic numbers are equal on the reactant and the product side. and the identity of the original or the parent element is going to be changed because your atomic number is going to change. And an alpha particle is a positively charged particle that is just the nucleus of a helium atom. For beta decay, the sum of the atomic masses and the sum of the atomic numbers are also going to be equal on the reactant and product side. But the atomic number of the daughter nucleus is going to be increased by 1, while the atomic mass of the daughter nucleus is going to remain unchanged. And our beta particle is going to be represented by the shorthand for our electron, an E with 0 mass and a -1 charge. And finally, our gamma rays have neither mass nor number because they're energy, they're photons, not subatomic particles. And the atomic mass and the atomic number of the original element are going to remain unchanged by the gamma rays. And we're going to represent our gamma rays with the Greek symbol for gamma and 2 zeros. And that does it for our discussion of radioactive decay. Bring any questions you have with you to class.